Hello everyone, welcome to the second presentation for the testing commissioning portion of this class. Today we'll be going over protective relay applications and a practical approach to relay testing. I'm your presenter, Cameron Grass. I'm a graduate of the EET program, class of 2019, and currently I'm working as a substation protection and control engineer with power engineers out of Hollowell. Firstly, we're going to be going over the purpose of writing up isolation procedures. Isolation procedures are used to specifically avoid misoperations, damage to equipment, or risk of injuries to any personnel working in the field. The isolation of the equipment means either on a large-scale sense by operating a breaker or switch to kill the load going through that part of the circuit, as well as isolating the secondary side, meaning the low voltage equipment in the control house or out in cabinets in the yard. This can be any form of DC or AC power that's being disrupted. So there's a standard sequence of operations for isolating a piece of equipment. In this case, we're going to be looking at a relay specifically to go along with the relay testing portion of this presentation. So the first step, as always, you want to get an outage request fulfilled and the equipment has been tagged out. This is usually done by communicating with the client in advance, coming up with a schedule, sticking to it, and then going through with it during the course of the isolation. Once you get the okay from the client or utility to proceed, this is how you go step by step to isolate a relay. So the first thing you want to take out is any of the critical outputs that may be in the circuit that you're isolating. This is done first specifically because a relay looks at the voltage and currents flowing in and out of it. If you disrupt any of those voltage or currents, the relay believes that there's an issue and it's going to send an operating signal to any of the breakers that are in that scheme. This is usually very bad because if you misoperate a piece of equipment that's not going to be a part of the outage, that could be detrimental to customers, to the client's procedures, everything like that. So by taking out the critical outputs first, you lose any risk, not any risk, but you lose most of the risk of any misoperations occurring. The second is the rest of your outputs. This can be any non-operative output that the relay may utilize. Next is communication-based tripping. This is usually any fiber, Ethernet, or any other sort of communication device that may operate a piece of equipment that may not even be at this station. This could be at another station altogether. So removing that gets rid of the risk of misoperating somewhere else. And lastly, that doesn't involve any power flow, would be your inputs. This is anything that the relay may be seeing from other relays, breaker statuses, switch statuses, etc., etc. And then the last two are your currents and voltages. Now, we specifically do currents first because that is where you will run into the most issues. If you remove the voltages, the relay may not pick up an issue. You always start with your currents and then end with the voltages. Getting into the specifics with your relay testing, firstly we'll go over some foundational HPI tools. HPI stands for Human Performance Improvement. This is something that is always strived for out in the field, and we're trying to implement it in the office space as well. HPI basically means how can we reduce the most amount of risk in the environment that we're working in. In the field specifically, this can be done by many different ways. First thing in the morning, when you show up on site, you get together with the crew and you go over the jobs that everyone's going to be doing throughout the day. That's what we call a pre-job briefing or a job hazard analysis as well. You communicate, you talk with everyone, you understand what their tasks are, what specific risks may be involved in those certain tasks, and figure out the best way to avoid working on top of each other, for sure. Project planning, this can be done before or during the phase of the field work, understanding what your tasks are for this specific project, whether it's a site that's already in service and going to be doing some equipment replacement, or it could be a brand new site being put together over the course of the next few months to possibly a year. STOP. STOP is an acronym that we utilize for procedures out in the field. Every time that something could go wrong or does go wrong, everybody needs to stop work, get together and analyze what went wrong or what could have gone wrong during the course of that phase. Phonetic alphabet. This is something that's used especially when you're doing your isolating. A lot of the relay test switches out in the field are usually labeled with the letters A, B, C, etc., etc. This is to make it easier to understand which switch you're specifically looking at or hoping to open or close. Utilizing the phonetic alphabet reduces the risk of someone mishearing a letter per se, and making sure that everyone is on the same page with what's going to be happening. Three-way communication, that is another thing that we utilize, especially during the isolation procedure. Somebody will be holding the prints, communicating to someone at the piece of equipment. They're going to relay that information. The person at the piece of equipment is going to relay it back to understand that they heard everything correctly and repeat it. And the person back on the prints will either say, yes, that's correct, or no, and go over it again. Questioning attitude, conservative decision making, effective communication, and stopping when unsure. Just all extremely easy HPI tools that you should be utilizing in the field that a lot of people just don't really think about unless something happens, which in that case it's too late. So PPE, or personal protective equipment, can be defined as equipment that you either wear or utilize to keep yourself as safe as possible, especially in an environment where you're dealing with high voltage, different factors if you're outside in the elements, stuff like that. Most common stuff that's definitely required when you go work or even visit out in the field is protective eyewear, which would be safety glasses that protects your eyes. Full-length FR clothing. This is extremely important because you're trying to reduce the most amount of skin that could be exposed to any flames if something were to happen. That got a little tough when I worked out in the field for 3 years, because some days it would be 98 and 100% humidity and you're out there in jeans and a long sleeve shirt just cooking. Gloves could be anything from cut proof, especially if you're working with sharp objects, to cut cables or wires, etc. As well as high voltage class gloves, which usually isn't something that you would work with as a testing commissioning engineer. That's more so the linemen that are dealing with the extremely high voltage line equipment. And the last one is rated footwear. That's usually EH rated boots, which stands for electrical hazard boots. The boots are rated for a certain voltage class to be able to protect you. Obviously, once you get into the extremely high voltage ranges, there's not much you can do. As well as steel-toed boots. That's for in case anything were to drop on your foot, just to protect yourself as most as possible. So what are we testing? In this example, when we're logging into the relay for the client, we're going to be looking at specific elements that the client's looking for. Certain stuff, metering, which is the phasing and analog inputs, measuring the current voltages as well as the phase angles of each of them. Specific relay elements such as pickup values and points for all set elements, timers, torque controllers, and blocks associated with each element as well. The inputs and outputs, the functionally tested inputs by applying voltages and testing all the outputs by verifying the logic they are set to. The inputs and outputs you test as a relay tech you're testing within the relay to make sure the relay correctly operates based on the surrounding isolated equipment, such as the knife blades and any lockouts or switches that may be in the scheme. These inputs and outputs also get tested by the testing commissioning engineers functionally, not necessarily by triggering the inputs and outputs based on the relay logic, but more so just to see that the circuit is made up correctly. And speaking on that, the protection logic, you test it to prove all logic using a mixture of analog injection and input manipulation with both the positive and negative tests. The positive and negative tests pretty much means that depending on the scheme, you want to make sure that the relay only operates for what you're trying to look for, meaning that if it operates on a trip output one way and then you test it to make sure it doesn't do it the other way, and it ends up operating, then you know it's a failed test and something needs to be looked at, whether it's in the relay logic itself or even in the circuits. As well as you're looking at the display, all the LEDs, push buttons, making sure that those line up correctly with what the client's looking for. So when you're prepping a test, you need to consider quite a few things, especially if it's an in-service relay. Take a save copy of as found settings. If this is an in-service relay, that means the relay has a settings file in there that was being used prior to whatever you're doing for upgrades. In case anything goes wrong or the client even possibly changes their mind about the whole job, you want to make sure you have the saved file of the as found settings, which means pretty much the file that's in the relay when you first get on site. This is also really beneficial when you're doing your testing to see that if something doesn't line up correctly during your testing procedures, you could possibly look back at the relay logic that was found in the relay to see if anything may line up or differentiate depending on what you're testing. You also want to run a compare against the new issued relay settings to provide for the client to show them, hey, this is what we found, this is what you gave us, and these are the only differences that are going to be issued. You also want to take an events report file. An events report is anything that the relay may have done while it was in service, meaning if there was a fault somewhere in the relay protection scheme and the relay operated specific outputs or sent commands or signals to other relays, it'll show up in that event report. And you also want to provide that to the client too, to also kind of cover your ass, because in case something were to happen during testing, you can show this to the client and say, hey, it wasn't me. You can see because the events report that I have right now matches with what I showed up with. So something else happened during testing that wasn't directly affected by us. The SER is kind of the same idea with more in-depth analysis of the relay elements. The events report pretty much dictates like something happened, and the SER is something happened, this was the elements that picked up and the outputs that operated. The SER is always going to be clear during testing because you provide the SER data to the client during every test, so you don't want 200 lines of SER data that doesn't even apply to what you're doing. The history, same idea, everything that the relay may have done while it was in service. This is all stuff that you absolutely want to do before you even think about plugging in your test equipment. Is the relay prepped? Did the new settings change LED designations or push button functionality? Are these issued for construction settings? The LEDs and push buttons, client dependent. Some of them, they actually don't even utilize the push buttons specifically. The LEDs are very common, especially to show what kind of trip occurred, whether it be a zone 1 trip or a differential or a lockout or a phase differential, anything like that. You want to make sure that the client is planning on utilizing either or both, as well as making sure that it lines up correctly with the template that the design engineer gave you. Pressing target reset button always will illuminate all LEDs and usually will reset them as well unless there's a standing trip or standing fault on any of the relay logic. These SEL templates are usually provided by the design engineer, but sometimes they'll just give you a list of what labels should go where for the LEDs and push buttons. And you can actually go onto the SEL website, look up the relay model that you're going to be testing, and get a front plate template from the website itself and fill out all the information necessary and print it off. The relays, when they get shipped out to these clients as well, will show up with like the it's not even like paper, it's more of a plastic like film that you put in between the relay front panel and the screen that covers it, and that's what you'll end up printing on, because it's much firmer and easier to get in and out of the front panel, because if you try to slide a piece of sheet paper in there, it's going to be a pain. So prepping your test for your connections, there's a lot of different ways you can hook up to the relay. Easiest way I found is if there are test switches available that hook up directly to the back of the relay. These test switches usually will hook up to both the inputs and outputs as well as all the voltages and currents. This is the easiest way to set up because the relay test set that you're utilizing will sometimes have these plugs that you can just shove right into the knife blades once they're all opened, and from there you can just plug in your cables to wherever you need it to go to the relay, and it's pretty simple. If the test switches aren't available or they're an older model that doesn't allow you to jack in with your plug, sometimes you have to go straight to the back of the relay, or if you're doing a bench test and the relay is not even installed yet, you'll have to connect directly to the back of the relay terminal blocks. This isn't terrible, but it can be time consuming and a little tedious to put your cables into every single output, input, voltage, and current terminal. It also gets frustrating to have to change the outputs depending on what test you're running, so it starts ending up being pretty time consuming. Specific tools that you're definitely going to need if you're going to be relay testing are insulated screwdrivers, multimeters, and a holding screwdriver. The insulated screwdriver is always utilized by testing commissioning engineers over just a standard like metal screwdriver. This is because you're understanding that the relay or any piece of equipment that you may be utilizing the screwdriver on should have no power, no voltage or currents running through it, or no DC feeds. But sometimes you never know. You could test with your multimeter and then seconds later somehow it gets power, and if you don't have an insulated screwdriver, then you could get shocked and possibly injured. The holding screwdriver is pretty much the same idea. It's insulated, however, it's not used for torquing. It's more so pretty much you can plug it into the back of one of those screws, and it ends up opening a little bit, so it has pressure on both sides and allows the screw to sit pretty much on it without having to use magnets or anything like that, which can also be bad, especially on power devices. What types of leads are you using? So what you see here are two very safer options of test leads for your multimeter. You can see that the top two pictures obviously are different models but have the same purpose. They expose the least amount of conductive metal on the lead as possible. This is really important because you want to avoid any possibilities of arcing, meaning placing a lead on one terminal that has power to measure it and accidentally having another part of the lead hit something else, whether it's the cabinet, another terminal to the relay, which can be detrimental because that could damage the relay, and that wouldn't be good because those are expensive. Or even possibly if your fingers are too close to the end of those test leads, if you touched it and tried measuring power, you might get shocked too. And the example down below is one with what seems like a very exposed test lead that has burn marks on it, meaning that there probably was a short, and quite possibly the lead might even have been longer. So back to what I was saying before, some of the test equipment that you may be utilizing can be super beneficial for speeding up the tedious process of plugging in your cables and all of your test equipment. The top picture is one of those test paddles that I referred to earlier. You can see on the back there, those prongs are what you plug into the knife switches, and your cables will plug in directly in the front. Again, it makes it super easy. You can just plug that in, put all your cables in. You can actually move them around depending on the test too, which makes life a lot easier during the testing process. But again, if you don't have test switches available to plug in the paddles, you'll most likely be utilizing these little forks down here in the bottom left. These are what you'll plug in directly in the back of the relay to the terminal blocks. Alligator clips, which you see in the bottom right, I actually don't necessarily think are a useful tool to utilize when you're relay testing, because the back of the relay terminal blocks, the screws are so small, and those alligator clips, unless they're super tiny, are probably not going to get a great connection, especially when you have to unscrew the bolt as much as possible. As well as, in this example, you can see that they're uninsulated, so that could also lead to damage to the relay or the test set, or possibly injuring yourself too, especially if the test set is pushing DC. We'll use color codes for testing quite often. The standard that I learned was red, white, and blue for A, B, and C phases. Those can be done for both currents and voltages. And then pretty much any other color other than those three for any outputs, inputs, other terminals. Barriers are extremely important. Those are pretty much any signage, caution tape, anything like that. You want to designate the area that you're going to be working in, because the test set you're going to be utilizing is going to be pushing DC voltages and currents and AC currents and voltages pretty much as long as you're testing. So you want to make sure that everyone knows that the area is marked off so that they don't unintentionally mess with the set and possibly injure themselves or damage equipment. Barriers are also extremely useful for designating the relay cabinet that you're going to be working in. If you show up on site and you've found the panel that holds the relay that you're going to be testing, you want to make sure that you barricade as much of the surrounding equipment as much as possible without operating anything for sure. This is just to make sure that if you say you go out to lunch, come back, and you don't even think about it, you just plug in your test paddle, some random relay, and start pushing currents and voltages, that might cause a trip, which could be bad. So this is the most standard relay test set that I think anyone working in the field utilizes. It's a Doble F6150. It's the most up to date. I think it's the easiest software to utilize as well, and it's extremely easy to set up all your cables. So you see in this blue section right here, and the red section as well, those are your current and voltage inputs. Those you'll connect to the current and voltage test switches or back of the relay terminal blocks if need be. The nice thing about those as well is that you can change them in the software. So you could actually flop them, have the currents be on the left and the voltages on the right, or even just have all voltages or all currents if you're doing like a differential test or something like that. Your logic outputs are here in the green. Those are what you'll be hooking up to all your relay inputs, because from the test set you're going to be operating something that the relay may want to see, sending DC voltage up into the relay input and then back out to the receiving end of the logic output at the test set. logic inputs, pretty much the same but reversed. You're going to hook these up to the outputs of the relay to make sure that the test set sees when the relay operates an output and make sure that it's the correct one. Your battery simulator here in the purple, that's actually your DC voltage that you can hook up to both the logic outputs and also power up the relay if need be. Usually if you're at a site and the relay's already in the cabinet and it's got all of its wiring installed, most likely you can run some tests to make sure that the DC feed is all set and good to go and supply the relay with DC from the control house panel. But sometimes that's not an option, especially if you're doing a bench test and you can power up the relay just utilizing the battery sim. The last one is all your communication plugins. You got Ethernet options, GPS, all kinds of different stuff. These are what you'll be, number one, plugging into the front panel of the relay to communicate, as well as plugging it into other devices such as a GPS clock, for example, which is utilized during end-to-end testing, which we'll be going over later. So when you're plugging in your voltages and currents, you always need to go look at the prints to, number one, point-to-point check that everything is lined up correctly into the relay and possibly test switches if available, and also understand what phase should go where when you're plugging in your relay test set. You also see, especially with the currents here as an example, the ratios that apply. This is something that you'll also be measuring as well. So when you supply 5 amps into this example here, the relay should see 3000 based on CT ratio that is shown in the circuit. And if it's not, then that's something that you mark, fix, and report back. This is what it would look like if you plugged it into the test set fully. You see all your voltages here on the left going in, your A, B, and C, which was designated based on the prints, as well as your currents over here, A, B, and C, per the prints. As you'll also see, again, for this example specifically, if these test switches are open, that means you only have these 4 points here on this line available. Terminal 9 on the knife switch, terminal 7 on the knife switch, and as well as Z01 and Z02 in the back of the relay. For the correct current flow, you need to make sure that when you plug in your primary feeds into here, that you jumper all 3 of these points over here to make sure that there's a current return for every single phase available. And once those are jumpered, you can just bring your black lead back to the test set. Analog connections, what could go wrong here? Again, like we talked about, if you don't designate your phase incorrectly, you're going to be running into a lot of issues in your testing phase and wondering what's going on and realizing your C and A phase are flopped or something like that. As well as making sure all the equipment is properly isolated and rated for the voltages and currents that you're actually going to be applying as well. So when we're doing our testing, most of the time when we want to pick up a specific relay logic element, something that doesn't trigger an output specifically from the relay, you'll end up hooking up one of your logic inputs to a spare output. In this case, it's polarity sensitive, so you want to make sure you're aware of that. But the reason we do this is when we're logged into the relay in the command prompt, you can set the spare output to equal whatever element you want to pick up. So what happens is when you run the test, that element that you're looking for picks up, it'll operate the output, and the test set will receive that output and mark it as a pass test. A lot of times I've run into this. You're running the test and you know the relay element's picking up because you're looking at the SER and you just forgot to set the output to whatever element you're supposed to. So the test is working, but your test set doesn't see it and thinks it's a failed test every time. So a lot of little things that you'll encounter if you're a relay tester that can scratch your head and you end up looking back and being like, oh, that was just so stupid. Most of the times as well, these outputs may not even be wired to any terminal blocks or knife switches in the cabinet. So you'll just have to go to the back of the relay again and plug it in. But that's not too big of a deal because you plug it in once and you probably won't unplug it again until you're all done testing. Instruction manual. That is your best friend when you're running into issues with your testing. It will provide all the information you need. You just got to look for it and understand how to apply it to your test. PDF versions are the easiest nowadays because you can just Control F search stuff, especially relay elements that you're trying to pick up or find. You can find the commands, word bits, reference equations for pickup testing or logic diagrams. Those are super beneficial because you may be missing something in your relay test setup that you won't figure out until you actually look back in the manual. You also look at the specs to make sure that you're not exceeding the limits to the relay and burning it up, because again, damaging a relay is an expensive mess up. Again, going over the limits, making sure you are aware of the maximum rating for different durations. This is especially prominent for the current ratings. Usually you won't exceed anything over 5 amps besides a fault scenario. So when you trigger a fault through your currents, you want to make sure you don't overload the relay or even the test set itself by exceeding the current limit. Understanding the accuracy range too. This is extremely important for making sure that your test will only pass if the relay picks up within the accuracy range. Again, this is all found in the SEL manual. Does a relay act different at different ranges? Meaning it might be a zoning type issue, or not issue, but more or less a different zone may have different fault currents, stuff like that. Some examples of challenges. Again, we talked about not setting that output, the spare output to the element you want to pick up, not putting in your test leads in the correct portions of the relays, stuff like that. Prepping your SER. You always, like I said, you always want to save a copy of the SER and then clear it. Clearing the SER ensures that when you run your test, the only thing that's going to show up on the SER is everything that's occurring during the test, meaning it'll see whatever relay elements pick up, outputs that may get triggered or operated, etc., etc. The SER will also show you if you're missing something. Again, if your test isn't set up correctly and the output's not operating, you'll see in the SER that that specific output never opened or closed. SERC is the terminal command to clear it. SERX, X being any of the relay elements, outputs, anything like that. Those will show you whether or not those operated within the last however long until it was previously cleared. Remember to move any added points prior to putting the relay in service. Again, this is especially important for setting up that spare output contact. If you set that up and you run your last test and you just unplugged everything and walked away, that output still has whatever relay element you put into it. Meaning if someone were to go back and run a different test or whatnot and see that that element's picked up for some reason, they're going to be questioning it. As well as if they don't do their due diligence later down the line and they end up utilizing that output, that could lead to a misoperation without even starting the relay testing, which would be really bad. DC schematic outputs. This is where you won't be utilizing the spare output contact. You're actually going to be making sure that the specific output is operating based on whatever test you're running. The isolation points, again, sometimes depending on the scheme, for example here, your trip coil 1 output and the rest of the spares actually lead to knife switches, but in this case, for the breaker failure initiate and the reclose initiate, they actually don't hit anything and they go right out to the terminal blocks and then possibly to another panel. So you got to be aware of when you're testing, making sure that everything is isolated properly, because if you, in this case especially, the breaker failure initiate, if you run a test to trigger this output and it's not isolated properly, the other side of this terminal block may go to another piece of in-service equipment. So if you close that contact in, you might trigger a trip scenario on 2, 3, or 4 other relays and could kill half or possibly the whole yard. Pulsing and measuring contacts is how you trigger them usually. This can be done in the command prompt or on the HMI terminal as well. Pretty much it just you set it for 1 second, the contact closes in for a second, opens back up, you make sure that everything that happened needed to. As well as you don't want to pulse a contact for too long. Usually 10 seconds is the max we'll ever do in the field, because if you hold that contact closed for too long, it might burn up, because it's usually only rated for a quick pulse and that's it. The inputs, again, what inputs are programmed in the logic, making sure that when you operate this other equipment, does it come into the correct input? Is it labeled correctly? Is it going to be showing up on the SER that it's actually a 52A status? As well as what causes the input to go high and low, and are there any limits? In this case, we can discuss the possibilities of messing this up again, because if you were to operate this lockout, for example, right here, this 5AH, this lockout, if you were to be testing it going all the way up to input 203 in the relay, that lockout could be connected to 2 to however many other pieces of equipment, so you want to make sure that that lockout is properly isolated and that you test it with the isolation points from every other possible contact. You also look at alarms from other relays that may be coming in. Again, these relays might be in service, so the only way to test them would be to isolate them completely and cause an actual relay fail to occur. This is all stuff that you always want to look over and understand what the risks may be, and then try to mitigate them as best as possible. In this case, with the breaker status, not a huge. Well, actually, if this breaker is in service, then there's actually no way to test this contact going up to the relay unless you were to take the breaker completely out of service, because the only way to operate this contact is to either open and close the breaker. So as long as it's completely isolated, that's easy. You just operate the breaker once, you see this input go high when the breaker opens, and then close it back in. See that it goes away. Like we said, the breaker failure, there can also be, in this case, it's a breaker failure transfer trip. So this lockout operates, sends a signal. The transfer trip may also send a signal to another relay, maybe in this control house or possibly another control house over the fiber lines. So again, understanding that everything that may occur when operating this contact is completely isolated and within the boundaries of the scope of work, then everything will be all set. But if you run into anything prior to operating this and testing the input, you always want to report it to the client and say, hey, do you want us to do this? Or just give them options. Like, we can test this, but we need to open its A, B, and C, and we need to kill the communications to this other site. Just coming up to them and saying, like, we can't do this isn't usually a good option, because they don't like hearing that. But coming up to them and saying, we can't do this right now, but these are our solutions, is a much better way of approaching it. Again, the relay fail alarm, like we talked about, if this relay is in service, can't test it, because if you issue a relay fail, from this relay, most likely it's going to operate every single piece of equipment that may be connected to it. So as long as it's out of service, you're good. Otherwise, might be worthwhile looking at a different way to test. Relay test mode. This isn't something that I went over earlier, but I guess I can mention now, especially prominent with the GE relays specifically. A lot of times when you're testing those, the relay won't even allow you to change any of the logic in it, meaning you can't set a spare output to whatever relay element you're testing, or even changing some of the logic itself, unless you put the relay in test mode specifically. Test mode pretty much means it's going to operate certain stuff, but it's not going to send any direct outputs unless necessary. Not as common in the SELs. SELs usually you can just plug and go, but definitely for GEs. In this case, when you're looking at a relay test mode, this one specifically is hooked up to an input, so you can go back and forth to make sure that the input comes in and out. That is all for today. I spoke with Paul hoping that we could get together and do a live session for the third and final presentation. Otherwise, if anyone does have any questions, please feel free to reach out. I'm always available and always willing to help out fellow students, especially through this wonderful program that you guys are a part of. So, thank you all for your time. I appreciate it, and have a good day.